Hello everyone, what's up? Welcome you all on this channel. Here is a brief profile about me. So, my dear friends, we will continue our lecture that is on hydrostatic forces and we'll cover the remaining topics. And this lecture is in line with our previous lecture. So, let us try to understand the hydrostatic forces on curved surfaces. So, basically, what the concept behind is and how to solve the questions that is on curved surfaces. So let's try to understand. So I'm drawing a 3D diagram. This is a circle, semicircle. Let us draw it properly. Straight line. This let's suppose this semicircle. Okay. And it is a cube. So how it will look like this. Go like this, right? Then there will be one line home. Straight line. So it will be a half circle and cylinder shape. It will go like this. And then there will be again one more circular shape, right? Able to understand this? And this is the fluid free surface and it will be completely filled with fluids. So this fluid, let us take this element here. So it will experience one force in the horizontal direction, right, Fh, and one force from the vertical direction, Fv. And combining these force, there will be one net force, that is F net, and it will be perpendicular on this surface, right? Normal to this surface. So let us try to understand and how to evaluate this Fh and Fv. So to evaluate Fv, I'll draw a side view of this diagram. So if I'll draw the side view, it will look like this. Side view, or I can say front view, right? And it will be filled with water, right? So let's suppose if I draw imaginary line here. So whatever the volume of water present above this fluid, that weight will be applied on this surface in the vertical direction. That will be nothing but Fv. So to evaluate Fv, it's very simple. You just see how much volume of water or certain liquid is there on the top of the curved surface, right? Till which point? Till you reach the free surface of that particular fluid, right? It's very important. So how will you evaluate Fv? Fv is nothing but rho g into volume. Volume of what? Volume of fluid above the curved surface till the free surface of that fluid. Okay. And now what is horizontal force? So it's very simple. You just try to make a projection here of this whole curve, right? So it will be a rectangle, right, on this surface. If I'll make a projection on this surface, so it will be rectangular kind of thing, right? If you'll see, it will be rectangular like this. So all the forces, whatever it will act, it seems like it is acting on this surface, right? If I remove this surface and keep it like this, it will be acting on this surface itself, right? So it will be equivalent to that. So you try to find out the force on this that we have seen earlier. What is Fh? Is nothing but omega area of that surface into x bar from the free surface of that fluid, right? Omega a x bar. A is the projected area of the curved surface on the vertical plane. Okay, so let us try to understand one by one. What is volume? What was volume in this formula? If V equals to OG into V, it is the volume of fluid above curved surface up to free surface of fluid. Very important line. Next thing was area. What was the area in that formula? In which formula? In horizontal. Omega A into x bar. It is the projected area of curved surface on vertical plane. Simple. What is x bar? X bar is the CG of A from free surface. That's it. So these are the basic formula. Let us try to solve this question. So now if I'll say this is the question where semicircle is having radius r and the height from the free surface is capital H and the density of the fluid is rho. So what is the FV and FH? So I draw the imaginary line. I'll calculate this whole volume and let's consider the width is B here for this. So what is this complete area? First I'll try to evaluate this complete area, right? So this area, that is shaded area, is A dash, let's suppose. So A dash equals to nothing but H plus R, this whole length, into R. This will give me the complete area of this rectangle minus, I subtract this area, right? What it is? Pi r square upon 4. Okay. So this is A dash. What will be the volume then now? A dash into B. So what is FV? FV is nothing but density into G into volume. Volume is nothing but A dash B, and I have formulated A dash H plus R into R minus pi r square divided by 4. This is A dash into B. So this is a final formula for FV. What is FH? FH is nothing but omega A x bar. A is R into B, means this projected area, right? This projected area. And then x bar is this projected area CG from free surface. What it is? Capital H plus R by 2 x bar. So if I evaluate FH, omega is nothing but rho G. Area is R into B, x bar H plus R by 2. So horizontal force simply evaluated. So let us move to our next question. So now if the question is given in this way, this is a vertical wall. Okay. Now the curved surface is like this. It is a semicircle again, and fluid is filled here. This is the free surface, and now we have to find out what is, it will apply some force right in this direction, and this will be having a horizontal component, a vertical component, FV and FH. So what is these two values are? Let us try to find out. Now I'll give you a, for solving this question, we know one method, right? above the curved surface, whatever volume is there, that will be the vertical force Fv. But here we can see that there is no fluid above this surface, right? So how to calculate then Fv? Because our previous formula or our previous method is not valid here. But anyway, like if we'll see here, this will surely will apply certain vertical force, but from the bottom, it is not from the upside. So to solve this, uh, and by having only one method in our mind, that is from top of the fluid. So let us consider that as a universal method. Let us try to convert this problem into this problem, okay? So that we can use this methodology universally everywhere. So how to convert this? For that, to understand the concept, let us consider this is whole water or that fluid. This density is rho, rho. Now if I say I have a curved surface, put it here, and it is an equilibrium state. Okay. So what will happen? Let's suppose this thing is in equilibrium state, right? So what does it mean? The force applied from here is equal to the force applied from this side. It means if I'll draw here a vertical line, so the force applied in vertical direction will be the fluid on the top of this surface by our previous concept, and this will be balanced by the vertical force by the fluid from the bottom line, right? So are you able to imagine if by any chance, if we ideally think that there is fluid here and having this free surface at the par of this level, right? Same level, free surface. So same this amount will apply the similar vertical force as applied from the bottom direction, Fv, right? So if we'll calculate this, means we are calculating Fv, right? And for evaluating this, we already know what it is the method. Fv is rho g into volume. So what is the volume on the top of this surface? So what is this volume? We have calculated already. So rho g, let's suppose this is capital R and I am having height h. So we have already calculated, right? R plus h into h minus pi r square by 4 into b, right? This is what we have calculated. Sorry, r plus h into h. Sorry, into r. And horizontal force, the same methodology. You just make a projection on the vertical plane. This is the projection. What is the xcg? It is h plus r by 2. Cg is h plus r by 2. And omega will remain same. A is nothing but r into b into x bar. X bar is nothing but h plus r by 2. So this is the answer for this question. So now you are able to understand, right? Even if it is in universal, like inverse direction, so what you have to do? You have to imagine a fluid that is on top of the curved surface having free surface as equivalent to the previous fluid, and by assuming it is on the top, you calculate the vertical force and it will balance each other. And how we understood like how these things will be balanced and equal. So now let us move to our next problem. So I have considered a cylinder of diameter d and length is B, and it is rested against a wall. This wall is fixed. Okay, and on the other side of this cylinder I am having a fluid. Okay, so the question says find the vertical force and horizontal force experienced by the sphere due to this fluid. Okay, so first as we can see, the surface that will experience the force will be this will be the surface which will experience the both horizontal and vertical force. So for calculating horizontal force, it's very simple. You have to take the projection of this on vertical plane. So this is the vertical plane, and projection will be rectangle whose one length is d and width is b. So omega into a, what is area of that projected area, d into b, right, into what is the cg, it is nothing but d by 2. So this will be the horizontal force experienced by the cylinder. Now coming to the vertical force. So as we can see here, now I have divided this surface into two parts, and as we can see the fluid is on the top for this surface, so it will experience a vertical force in downward direction, that is Fv1. And as we can see the fluid here, it is in the downward direction of the cut surface, so it will apply a vertical force in upward direction, let's say Fv2, and we'll calculate these two forces separately. Okay, so let us consider this curved surface first. So above this curved surface till free surface of the fluid, this is the amount of liquid above this curved surface, and I want to find the volume of this, and we can calculate Fv1, right? So what is Fv1 then? Rho g into volume 1. What is volume 1? Is nothing but this area into B. What is this area? Complete square area. Let's suppose the radius is r. Complete square area is nothing but r square, and minus this area, what it is, pi r square upon 4 into B. So I have calculated this rho g into r square minus pi square divided by 4 into B. This is Fv1. Now I have to calculate Fv2. Okay, so this is that curved surface was like this. Now I have to calculate this curved surface, right? And the fluid is from the bottom. So what I'll do, instead of this, what I'll do, I'll above this curved surface I'll assume imaginary fluid, right? Like we did in the previous case. So this is the imaginary fluid above this surface. And the force applied by the fluid below this cursor will be same as force applied by this fluid, weight of the fluid in vertical direction. So simply we can calculate Fvt is rho g into volume of this whole fluid. What is the volume? R square plus pi square divided by 4 into B. So net vertical force Fv2 minus Fv1. So this will be in upward direction, because F_V2 I have considered as a positive, upward as a positive direction. So F_V equals to rho g into r square plus pi r square upon 4. B will also common. So minus r square plus 4. Finally we get rho GB pi r square divided by 2. Answer. So I hope this concept is clear to you all. In case of any doubt, you can ask in the comment section of this video. So I'll give you a question for your homework. You try to solve that question. Okay. In case of doubt, you can ask me. So I'll describe the question here. You try to solve. This is like in future, this question might be asked. Okay. So let us see. It is based upon the previous concept that we have learned. Semicircle here. And the fluid is filled till here in this tank. And this semicircle is hinged about this point. Okay. And the radius is r. CG will lie somewhere here. What will be this distance? 4r upon 3 pi. So now the question says that to maintain this gate at this particular position, what will be the force required here? What will be the force required to maintain the gate in the given position? Right? So that is the question. So how will solve? See, this gate will experience two forces, one in vertical direction and one is horizontal direction, like we have seen earlier, right? What is this surface? This surface has got two forces, one in the horizontal direction, another in the vertical direction. So what will be the FH? FH will be applied somewhere here at the center of pressure in this question. Similarly, the FH, the horizontal force, will be applied somewhere here about the center of pressure. You have to evaluate that. Okay. And then the force, vertical force, FV. FV will be applied here. Okay. From the center of gravity, about this point, FV will be applied. So now if I'll try to balance the moment, so F into 2R, this is in the anticlockwise direction, plus FH into H bar, that is center of pressure from the free surface, equals to FV into 4R upon 3 pi. So from here I can calculate F. So for that you have to calculate FV, you have to calculate FH. So similar, like the method that we have applied here, you can calculate based upon that. Okay, similar logic. And the center of pressure H bar, it will be nothing but 2 upon 3 into 2r. You can also evaluate this, how much the center of pressure is. So with this, the hydrostatic forces on curved surface topic is completed. In case of any doubt, you can ask in the comment section of this video. Thank you all for watching this video. For more videos and regular updates, subscribe to this channel. Thank you all.